it is now recording. Okay, so this is section 6.3, properties of the trig functions, properties of the trig functions. Today we're going to do the sine function and the cosine function, and we'll probably save tangent and the reciprocal functions for Tuesday. But the test is going to cover them all. If you understand sine and cosine, you're going to be pretty good when it comes to tangent and the reciprocal functions. Okay, so what do we mean by the properties of a function? Things like domain, range, technically zeros. We're going to hold off on zeros for a little bit. Is it even or odd? Right? Today we're going to talk about a property you haven't seen before, and that's the period of these functions. I've got my calculator here. You should probably have yours handy to mimic what I'm doing. Let's start with the sine function. So we can say y is the sine of theta, although that's going to be a little misleading because we're also going to talk about the cosine of theta. And if I were to put that on the board without any explanation, you would be saying, Bosquet, you're wrong, because the cosine is the x, but I'm going to call it y, which is going to get really confusing. So let's, instead of saying y, can I just call it f of theta and f of theta. So these are functions, right? Functions of theta. When we actually get to the graphing, which is in 6.4, and you know, we can look at graphs here if we want. If I put in the sine of, now I can't put in theta, right, because I'm in function mode, and the calculator insists I use y and x. That's the way the calculator works. But when I look at this picture, there's actually a special window for that. I get this wave, right? And that's the first picture I'm going to draw up here on the board. This now is the sine function. You actually saw a picture of it on your last test. Remember, there was a question, was this even or odd? Right? So, and you had never seen it before, but I said just by looking at the graph, I can tell that this is odd, right? It's symmetric about the origin. This is an odd function. Let me put some numbers here. The tops of these waves are at 1. The bottoms of the waves are at -1. And this wave continues forever, right? It just keeps going like this. If I open up the window, right, and zoom out, and it just goes on forever and ever and ever, right? If you know that, what do you think the domain would be? All real numbers, right? So all reals, or -infinity to infinity. Now what that means is, remember, the domain is this independent variable. This is the theta axis, and this is the f of theta axis if you want. This up here is f of theta, or the sine axis. And you're going to say, why don't I call it the y-axis? I could. I don't want to. I want to call it the f of theta axis, the sine. And this says, as theta changes, as theta keeps going out, right, the y value, the sine value, keeps oscillating. Right? Let me get rid of that. I can put the sine of any angle that I want. Right? I can put the sine of 303,678. I think I'm in radians here. Yeah, I am. Radians. And it comes out to that number, right, 0.72. I could put the sine of -23,604.23 radians, and it comes out to that number. Okay? You can put in, you know, any angle in radians. You can put any angle in degrees. It doesn't matter. If I want to do 236,954 degrees, I can do that. Actually, just put a degree symbol in, and it comes out to that. Okay? What do you notice about all those resulting functional values? They're all between, right, and so that would be the range, and the range would be between -1 and 1. How do I write that in interval notation? Bracket, -1, comma, 1, always from smallest to largest, right? So that's the range. One of the unique things about this function is it has a tendency to repeat. So if I could take this section and just sort of drag it along, it repeats right here. I get the same picture. Or if I drag it this way, it repeats over here. We're doing it right. And in fact, if I, let me draw a new picture. Say I had, get rid of that thing. Say I had a set of axes, and I just draw one section of the wave, so it looks like this. And then if I could somehow copy that and then paste it and put it right here, right? And then paste it again. Now, obviously, this is one of the things you can do in digital stuff. And paste it again. Make the teacher look dumb. The graph just keeps repeating. Now, the question is, why would that be? What's going on here? And it has to do with the unit circle. So I came up with sort of a goofy analogy in the other class, but I thought it was useful. First time I thought of it. Suppose you're on a Ferris wheel, right? And the Ferris wheel is sort of goofy because it's built so that this is ground level. This is 0. And the Ferris wheel actually goes down into a trench. It goes below ground, then it comes above ground, right? And this is the Ferris wheel car, and it goes around and around and around, right? Now, if you're in the car, and I said, how high are you at that point? You would say, give me a number. 0, you're at 0. And let's suppose this went all the way up, and it was one unit, one big distance, I don't know. So at the top of the Ferris wheel, you're at 1, right? And as you travel around, now you're back to 0. And as this goes around, it just keeps repeating over and over and over again. Oops. Over and over and over again, right? Well, that's what this wave does. If I put a point here, and let me put some numbers just to make it obvious. This is pi, this is 2 pi, this is 3 pi. By the way, when we get to the graph part, that's going to be section 6.4. You need to know those numbers. Those are called those numbers. Those are called say again? Well, I know, but what's so special about them? Say it again? Well, they are x-intercepts. They're called begins with the letter Z. The zeros of the function. Those are the zeros of the function, right? Because that's where the graph hits the axis every time. Okay, so if this point is representing this red dot, and here I am at 0, by the way, this is 0 degrees or 0 radians, right? I'm sitting right there at 0. And then I start to move the Ferris wheel, and I get up to the top of the circle. By the way, how many radians is that? Up to the top? A half a pi, right? I mean, I know it's 90 degrees, yes? Is it 90 degrees half a pi? Remember your calzone, if you had to split it in half? Okay. So that's half a pi. The dot there corresponds to the dot here. It's right at the highest part of the Ferris wheel. Here we go. Okay, so now the car comes back down, and it lands here. What's the angle? What's the angle? Pi, which is the same as how many degrees? 180 degrees, right? So you've gone all the way halfway around, and now the dot's sitting right there. Right? So we travel around again. Now we've got one full rotation, and that gets us, whoops, That gets us all the way back to there. Okay? So, and then after that, this graph just keeps repeating. This is the period. This is the whole idea. This is a periodic function. Probably one of the more confusing things in your book when you read it. It's on page 397. Page 397. And it says the sine of theta plus 2 pi k equals the sine of theta. This is talking about the period of the sine function. K is any integer. Okay? K is any integer. And what this says, if you're at a certain angle, like say we have a certain angle, here's your Ferris wheel, here's some angle, and it happened to be theta, I don't know, call it theta. And here's your car, and you go, oh, this view is perfect. I don't want to be anywhere else except right here. Oh, shucks, the car moved. When you get back to that location? Go around. How many times? Once. Just make one more rotation, and you'll end up right back at that same location. Right? There's that view again. It's perfect. The sine of theta, the y-coordinate there, is exactly the same as the sine of theta plus a rotation. What's one full rotation? Don't tell me 360 degrees. 2 pi, right? 2 pi. Okay, so here's one more rotation. But it doesn't have to be one rotation. It could be any numbers of rotations. And that's why it says 2 pi times k. K could be 0, k could be 1, k could be 2, k could be... The sine of, I don't know, 0.236 radians is that. Okay? The sine of 0.236 plus 2 pi. So now I've added a full rotation. You know what number I'm going to get? Exactly the same number. There. I can add 2 pi times anything. So I can do, there's my theta, there's my 2 pi. Let me do 2 pi times any integer. I can do 9, I can do -9, I can do -97. It doesn't matter. Any integer I put there, I'm going to get that same sine value. Okay? The sine function is periodic. You just keep adding 2 pi's and you get the same number all the time. Okay. While I'm here, let's talk about even odd. This angle that I've shown is a positive angle. Why? It goes counterclockwise. That's what makes it positive, not the fact that it's in quadrant 1. It has nothing to do with whether it's positive or negative, right? I mean, this angle here also goes in the first quadrant, but that's some negative angle, right? Okay. Let's look at a negative angle that's the same size as this, but going in the other direction. So this angle now is negative theta. I mean, if you want to think degrees, you could. There's positive 30, there's negative 30, right? And look at the dot here. What can you tell me about the coordinates of these two green dots? Are they the same? Same. The x values are the same? How come? Give me a word beginning with V. Vertical line, right? They're on the same vertical line. Correctamundo? What is so interesting? Golly Moses. Oh, I'm doing so well because my quizzes are great. The test is 60% of your grade. Quizzes are 20% or 30% of your grade, right? You go bombing tests. It doesn't matter how many quizzes you get. 100 A plus on all the quizzes, 0 on all the tests, and you're sitting at, let me think, that would be 30%. You fail. Yeah, this is x and y. This is x and minus y, right? If I talk about the sine of theta and the sine of negative theta, are they the same? He puts a question mark there. Are they the same? No, they're not the same, right? This one's some positive number. This is some negative number. Is there any relationship between those two things? Okay, well, let's go to the x first, and then we'll go to what I'm looking for. If I said the cosine of theta and the cosine of negative theta, are they the same? They are the same. The x-coordinates are the same. Yeah? Okay, so we're going to come back to that in just a sec. But what's the relationship here again? Negative opposite signs. They're opposites. Okay? So, I mean, you know, if you're doing 30 degrees, like on your little quizzy thing, if this was 30 degrees and you put in the square root of 3 over 2, square root of 3 over 2 and 1/2, and down here you put in square root of 3 over 2 and minus 1/2, right? The y-coordinates are opposites. That's what this says. By the way, that is the definition of an odd function. You may have to go back to your book. I don't know where it is, chapter 3, 2, 1. The definition of an odd function is if of negative x, that's odd. Now, whether you put the negative sign there or here, it doesn't matter. Sometimes you'll see it this way. It might be interesting for somebody, anybody, get a bonus point or something. Find the page number where the definition of odd function is. The sine function is an odd function, okay? So the sine of any angle is, in fact, the opposite of the sine of the negative angle. And again, you can put this negative sign here, or you can put it over here. Doesn't matter. Okay, so yes, sines are odd. Okay, so we got domain, we got range, we got period. And maybe we should just write that, the fundamental period, because you'll see that word is 2 pi of the sine function. Now, once you have all that figured out for sines, cosines are almost exactly the same. There's one change. Let me do cosine. If I throw in the picture and go, here's the cosine function, and this is at 1, and this is at -1, right? And this goes on forever. You want to talk to me about domain? Right, all real numbers, any angle you want. How about the range? Right, bracket, like that. And just like with the sine, same thing. Okay, you know what the period is? You're on a circle. Period is 2 pi, still the same. This is my fundamental period, that piece. When we talk about wavelength, like say we're a surfer and we're concerned about what the wavelength is out in the ocean, it's from crest to crest. That's wavelength. So wavelength. On this function, it happens to be 2 pi. And if I could take that and just copy it, put it here, right? And copy it again, put it here. But yeah, it repeats every 2 pi. Now, whether you go wave top to wave top like that, or whether you do a different section of the wave, you could go from here is 2 pi. That's the wavelength. Okay, and I could take that and again repeat that and get the same picture. So the fundamental period is still 2 pi. So you might want to write that down. Fundamental period is 2 pi. For sines and cosines, domains and ranges are the same. There's some problems in the book about finding trig functions of weird angles. One of the ones I did in the other class I thought was interesting. And I'll put the homework together tonight for you to play with. It says, what's the cosine? The cosine of 33 pi over 4. And you don't have a calculator, so throw my calculator down in the tray. No calculator. How do you calculate it? Well, you know, the way we did all these things was we figured out where on the circle we are, right? But that's not one of my standard angles. That's like going around and around and around and around and around, right? So we're in the Ferris wheel again. And if we just go to there, halfway up, 45 degrees, what's the angle in radians? Pi over 4. Okay, so we've taken our calzone, right? We split it in half, That's 1/4, 2/4, 3/4, 4/4, right? So this is pi by 4. This is 2 pi's by 4. Now I know I'm not going to write it that way. I'm going to write, instead of 2 pi's by 4, pi over 2, right? This is 3 pi's by 4. This is 4 pi's by 4, which we're not going to write as 4 pi's by 4. We're going to write as pi, right? 180 degrees. This is 5 pi's by 4. This is 6 pi's by 4, which we're not going to write that way. How do we write the bottom of the circle in radians? 3 pi by 2, right? This is 7 pi's by 4. Boy, this is getting tedious. This is 8 pi's by 4. By the way, 8 pi's by 4 is 2 pi, which is 1 rotation, right? We're back to 1 rotation. 8 pi's by 4. So I got to keep going. I got to get up to 33. This sounds crazy. Well, okay. So there's 1, 2, 3, 4, 5, 6, 7, 8 pi's by 4, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. I end up right there. Do I have to count that out every time, Bosque? No, of course not. There must be an easier way. I mean, what happens if this, instead of 33, this was 537 pi over 4? Right. There's no way in creation you're going to count all the way around. You'll lose track. So how do we do it with numbers? What can we do with that? Let me ask this question. How many pi by 4s, that's sort of weird, pi by 4s are there in one rotation? Question mark. How many? 8, right? 1, 2, 3, 4, 5, 6, 7, 8. 8 pi's over 4 is the same as 1 rotation. Yeah? And so the question is, what's the cosine of 33 pi over 4? Well, here's one approach. I could just take 8 pi's away from that, 8 pi's over 4. This is the same as the cosine, let's see, 33 take away 8 is 25 pi over 4. 25 pi over 4, Joe. Or I can take 8 away again, just back up another rotation. 25 pi over 4 take away 8 pi over 4 is 17. Take away 8 again. 9 pi over 4. Take away 8 again. Pi over 4. By the way, that was the question on the quiz, right? Do you know the ordered pair? Square root of 2 over 2. Wasn't cosine the x-coordinate? Didn't I ask for all those things? Yeah. Okay. As you play with these over the weekend, you've got 3 days to do this. Think of some creative ways. My suspicion is you're going to divide this by 8. 33 divided by 8. I don't care how many times it goes in. That's just the number of full rotations. I want to know what's left over. 8 goes into 33 4 times. How many left over? 1, right. So there's my full rotation, and that's what's left over. So this is the same as this. Just put a 1 there, right? 1 pi over 4. Okay, you'll play with some of these as we go through. The even odd properties are on page 404. You can look at those. Finding values of trig functions. We'll do some exercises. I would suggest you read the book, look at some of the examples, right? And I will assign the homework problems. You can start working those. I'll try to do all the problems tonight, put them up so you can check yourself as you go. The test questions are going to be very similar to the homework questions. I may just go into the homework that you've been assigned, that hopefully you've worked, and I'll just say, here's problem 7, here's 32, and same problem. Amen. Our Father, who art in heaven, hallowed be thy name. Thy kingdom come, thy will be done, on earth as it is in heaven. Give us this day our daily bread, and forgive us our trespasses, as we forgive those who trespass against us. And lead us not into temptation, but deliver us from evil. Amen. Okay, have a good weekend.